my name is Shivani. I'm a new Wyzant tutor here, and I'm here to help with your physics problem. I'm going to share my screen here. All right, so for the first question, we have three charges, positive 10, positive 20, and negative 30 microcoulombs. They're located at negative 1 meters, the origin, and positive 2 meters, respectively. And the question asks to find the net force on Q2. So let me just share my work here. So this is the setup. I have drawn the three charges here. I've also wrote down the electric force formula, which is K times Q1 times Q2 over R squared, where Q1 and Q2 are the magnitudes of the two charges, and then R is the distance in meters between the charges, and the constant K is 9 times 10 to the 9 newtons times meters squared over coulomb squared. So the net force on charge 2 will be the vector sum of the forces exerted by Q1 and Q3. Now, this force formula requires the charges to be in coulombs and not microcoulombs. So we can simply convert those. So note that 1 microcoulomb is 10 to the negative 6 coulombs. So Q1 will be positive 10 times 10 to the negative 6 coulombs. Q2 would be positive 20 times 10 to the negative 6 coulombs. And then Q3 would be negative 30 times 10 to the negative 6 coulombs. So the force on Q2 by Q1 would be equal to K times Q1 times Q2 over the distance squared. So it would be equal to 9 times 10 to the 9 times Q1, which would be 10 times 10 to the negative 6 coulombs times 20 times 10 to the negative 6. And the distance between the two charges would be 1 meter, so it would be 1.0 meters squared. And then if you plug that into your calculator, you would get you would get 1.8 newtons. Now, the direction of the force depends on the magnitudes of the charges. Q1 and Q2 are both positive charges, so Q2 would experience a repulsive force from Q1. So the force on Q2 by Q1 would be directed away from Q1. And in this case, that would be to the right-hand side. So we can go ahead and draw this force vector right here. I'm just going to label it F on Q2 by Q1, which is 1.8 newtons to the right. Next, we can calculate the F on Q2 by Q3, and using the same formula, so it would be K times Q3. Now, Q3, we only need the magnitude, so it would be 30 times 10 to the negative 6. We can ignore the sign when calculating the value of the force, but the direction of the force depends on the signs. In this case, it's a positive and a negative charge, so there would be an attractive force. So let's go ahead and calculate the magnitude of this attractive force between Q2 and Q3. The distance would be 2 meters between Q2 and Q3. And then the value of this force, we plug it into the calculator. Let's see what it would get. So here we would get 1.35 newtons. Now, like I mentioned earlier, the force here would be an attractive force between Q2 and Q3. So Q2 would be attracted to Q3. So the vector between Q2 and Q3 force would be directed to the right, towards Q3. So I'm just going to draw that vector right here. And this is going to be F on Q2 by Q3, which is 1.35 newtons to the right. And it would be directed towards Q3 to the right. All right, so now that we've got the two force vectors on Q2 by each of the two charges, we are ready to calculate the net force. So the net force would be the vector sum of these two forces. So net force. Now, since the two force vectors are directed to the same direction, or to the right side, we can simply add their values. So net force would be 1.8 newtons plus 1.35 newtons. And that would be 3.15 newtons to the right. So 3.15 newtons to the right is our final answer. And going back to the question, that would correspond to choice A, 3.15 newtons to the positive x direction. So that means to the right side. So the answer will be choice A. So now we can move on to the next question. Let me see what this is here. All right, so now we need to calculate the magnitude of the net electric field at a certain point. So it's asking to calculate the magnitude of the net electric field at the point +1 meter, 0. Now, I have used a slightly different setup for this, but it's overall kind of a similar approach. So let me just open it up. So this is the electric field setup. Now, the charges were in the same place as last time. We have the 10 microcoulomb charge at -1 meters, the 20 microcoulomb charge at the origin, and the 30 microcoulomb charge at +2 meters. And this I've labeled as point P. That's the point where we need to find the net electric field at. The formula is K times Q over R squared, where Q is the magnitude of the charge and R is the distance between point P and the charge. Now, a note about the direction of the electric field vector. Hang on. So the electric field is always going to be directed away from a positive charge and toward a negative charge. So that's just something to keep in mind when we draw our electric field vectors. So the electric field at point P is going to be the vector sum of the electric field of each of these point charges, Q1, Q2, and Q3. So the electric field by Q1, so let's go ahead and start calculating these. So E Q1 at point P, that's going to be equal to 9 times 10 to the 9 and again the charge has to be in coulombs, so just like before, Q1 would be equal to 10 times 10 to the -6 coulombs over the distance squared. So the distance between P and Q1, so let's see, there's 1 meter between P and Q2, and then 1 meter between Q2 and Q1. So the distance would be 2.0 meters in this case. So the electric field from Q1 at point P, let's plug that into the calculator. So it would be 2.25 times 10 to the 4, and then the units, let's see what the units would be. Newtons per coulomb, that's usually what the units are for electric field. Now let's find out the direction. Now the direction is always going to be away from the positive charge. So in this case, it would be directed to the right. So let's go ahead and draw that vector. I'm just going to write down EQ1. So it's going to be directed to the right or away from the positive charge. Now let's do the same thing and calculate EQ2. So EQ2, so it'll be 9 times 10 to the 9. Times 20 times 10 to the negative 6. Over the distance squared. So the distance in this case between P and Q2 would be 1.0 meter. So when you plug this into the calculator, let's see what we get. So we would get 1.8 times 10 to the 5 newtons per coulomb. And it would be directed away from the positive charge, so it would be directed to the right. So this is EQ2. All right, so now let's lastly calculate the electric field from Q3. So remember, it's going to be pointed towards Q3 since it's a negative charge. So it's also going to be pointed to the right direction. So we can go ahead and calculate that value. Let me just make some more room here. So EQ3, so you have 9 times 10 to the 9 newtons times meter squared over C squared times Q3, which is 30 times 10 to the negative 6 coulombs. The distance would be 1 meter, so you have the distance between plus 1 meter, plus 2 meter. So let's plug that into the calculator. So it'll be 2.7 times 10 to the 5 newtons per coulomb to the right. All right, so let's label this as EQ3. So now that we determined the values of each of the electric fields exerted by each of the points, we can calculate the magnitude and the direction. So the direction, they're all directed in the right, so the magnitude is simply going to be the sum of all of the electric fields. So the net electric field So it will be E of Q1 plus E from Q2 plus E from Q3. So it would be 2.25 times 10 to the 4 plus 1.8 times 10 to the 5 plus 2.7 times 10 to the 5 I'm plugging it into my calculator. Okay. So the total will be 4.725 times 10 to the 5 newtons per coulomb to the right. Now let's see what our answer key says, or our answers are. So we ended up with 4.725 times 10 to the 5. So the answer would be choice D. All right, so there you have it. That's our final answers. So yeah, that's the solution with the explanations. And if you have any questions, feel free to leave me a comment in the question that you posted. And I hope this helps. Thank you.